In the previous class, we concluded chapter 4, finally. It's the process architecture. So the computer systems, so I believe I already mentioned in the chapter 1, the computer system is briefly, so that means the briefly, so there are many components in the computer systems, but briefly in the computer systems, the main components of the computer systems are processor and memories. Okay, actually the memories include storage systems because our data is stored in memories. Then in the chapter 5, we will learn about memory systems. So in chapter 4, we learned about processor architecture. That is also called the processor. But usually the processor is not called a system. But in chapter 4, we learned about processor architecture, and in chapter 5, we will learn about memory systems. Okay. So, okay, I will introduce about the memory systems. So, what is a memory system? It's a system of lots of memories. So I said we store our data. Actually, all kinds of data is stored in memories. So in the computer system, or in a typical computer system, what are memory systems? That means that what are components of memory systems? So actually, in chapter 4, we learned about the process architecture, but as you know, this process architecture also includes memories. What kind of a memory? What are the memory components in the process architecture? So in chapter 4, we learned about the process architecture. So in the process architecture, what are the data path elements? So like instruction memory, register file, ALU, data memory, and then other components such as sign extension unit, boxes, multiplexers, and or hazard detection unit or some other units. Okay. So, but if we just see the data path element in process architecture, we can find that this is a memory because the instructions are stored in instruction memory. So it's called memory. So instruction memory is also memory. And how about the register file? Register file is also memory because the data is stored. So the data is stored in the register file as some register data, register operands, and then this data is read from the register file also. So that means that the register file is also memory. About the data memory, it's also memory because our data is stored in this data memory. So in the chapter 5, we will learn about the memory systems in computer system. In the computer systems, yes. So actually, we if we open some cover of our desktop computers, or so actually our laptop computer is also the computer systems, and then actually our smartphones are so typical computer systems. So if we just open the cover of our laptop computer systems or smartphones or desktop computers, then we can find many different kinds of memories. So usually we can find main memory. It's called the main memory. So actually it's a DRAM. And then, so we already know that the data stored in Dram is removed if power is off. So that means that the power supply is disconnected, then the data is erased. And then in order to avoid this case, we need the storage. Then we usually SSD, solid state drive, or hard disk drive as a storage media. So we can find the many flash memories in our smartphones. Okay. So actually, these are also memories. Okay. So in the process architecture, we learned about the register file, instruction memory, and data memory. And then in our actual computer systems, we can find many different types of memories, like main memory and storages. So that means in our computer systems, there are many different kinds of memories. Okay, the first, different kinds of memories exist in our computer systems. So we need to organize these different types of memories in our computer system. And then, so we need to manage how data is accessed from the memory. Okay, so why is this important? So it is critical for performance of computer systems. Okay, so it's very important actually. So in chapter 2, I explained that it's some processor model. So actually it's the computer system model. So computer processor receives instructions and this computer processor changes state of computer systems. And then I mentioned that the state means data inside of computer systems. So if we just focused on some typical instructions like X1, X2, X3, so this instruction, the add instruction requires data. So the main purpose of our computer processor or computer system is that the data is read from the memory, and then with this data is processed, and then results are stored in the memory, and then we can use these results. Okay. So first, data is read, and then data is processed, and then data, this result, is stored. So actually, the main purpose of the computer system is that the data is processed, and then the result data is generated. That's why data is so important in our computer system. And then this data is stored in the memory systems. So this second purpose. So how to read or store data in this memory systems is very critical for performance of our computer systems. Okay, so we will learn about these memory systems in chapter 5. Okay, so and then people moving on the memory systems, then I will explain about the locality. So actually this locality is a very critical characteristics of our data used by normal applications. Okay, so it's a very critical characteristics of our data. Okay, and then I found that this locality is translated into 지역성 in Korean. What does that mean? But it's not, this Korean terminology is not easy to understand the meaning of the locality. Okay, so if we just so try to understand the locality as the the characteristics of our normal data. So just understand. So just understand. So locality means that if a data is used by our processor, then this data, so the same data, or adjacent data, so that means the neighbor data, will be frequently used or reused with high probability. Okay, so in other words, so that means that if some part of data is accessed by and then used by processor, then the same data or some neighbor data, so adjacent data, will be used or reused in the near future. Okay, so that means that so that is the meaning of locality. Okay, so just remember that locality means that a certain data is used, so that means that it's requested by a certain instruction, and then the same data or some neighbor data will be used in the near future with a high probability. So data will be reused again and again by the same application. That is called the locality. Okay. So just think about your code. So your basic code. So like A equal 1, B equal 2, C equal A plus B, and then D equal A minus B, blah, 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 blah. So if a certain data is defined by programmers in the high level code, then this defined variables will be used in the near future, but like C equal A plus B and then D equal A minus B. It is because we define variables in our code because we will use these variables. So data is defined and the data will be used, and then this data, so or some neighbor data will be used again and again. That is the property of locality. So there are two kinds of locality, so temporal locality and spatial locality. So if we just see that this word temporal, so temporal means it's the time. So temporal locality means that if a certain data is accessed by a processor, then the same data will be re-accessed. So it's the same data. The same data is, so data is accessed. So that means that it is called the referenced. Okay, so that means the referenced means that a certain data is used by an application or a processor, and then the same data will be referenced again. It's called the referenced. So that means that the same data will be reused with a high probability in our code. That's same. So just to imagine that if you just define a certain variable in your C code, like A equal 1, and then this variable will be used again and again in your code, right? So that's the temporal locality. Okay. Also, we frequently use iterative loop, like a for I equals 0, I is less than 100. So this is the iterative loop. So we just frequently use this iterative loop. So instructions in this iterative loop are used again and again. So and then these instructions are stored in instruction memory. So instructions are also data. So instructions in a loop are referenced again and again. So that shows temporal locality. So temporal locality means that the same data is referenced again and again. Okay, and then spatial. So spatial means that, and then it's called spatial means space. Okay. So spatial locality means that if a certain data is accessed by a processor, neighbor data, so like adjacent data, will be accessed in the near future with a high probability. So spatial locality means that the neighbor data will be accessed in the near future. And then, so it will be frequently found in our normal applications because we frequently use the arrays like A100. And then if a certain element of this array is used, then we will use the neighbor elements. Like if A0 is accessed by our code, then with a high probability, then we will access A1 in the next loop or in the near future. So this example exhibits the spatial locality. So certain data is used, and then the neighbor data will be used, referenced in the near future. Okay, so that is the spatial locality. So this is the example of the spatial locality instruction. So if we just see the instructions, then PC is just increased by 4, like, and then if a certain instruction is fetched from the instruction memory, then next instruction will be fetched like 0 PC address 08. So instructions are sequentially fetched from the instruction memory. That means that a certain instruction is fetched, and then the next instruction is the neighbor data. So neighbor data is referenced. It's called the spatial locality. So it's also array data, as I explained. And then usually if we just declare some different variables in our C code like A, B, C, D, and then usually this data is stored in the some near location of the memory. Okay, so the address of the A is, so that means that the address of A may be similar to the address of B or address of C. Okay, so this is the spatial locality. So just remember that these two types of localities. So this locality is frequently observed in our normal applications, and our memory systems make use of temporal locality and the spatial locality to improve the performance of our computer systems. Okay, so that's why the locality in our data is very critical for the performance of normal computer systems. Okay, and then also, so we will learn about the memory hierarchy in chapter 5, and actually the memory hierarchy make use of locality in our data. Okay. Okay, then let's see how we can take advantage of locality. So memory hierarchy. So I will explain about the memory hierarchy, but think about the normal computer system you use. Okay. So where is our data? So where is our data? So actually our data is stored in storage devices like SSD or HDD. So, and then if the computer is turned on, then data inside of this SSD or HDD is transferred to the main memory, DRAM. And then we already know that. So in the chapter 4, we learned about the process architecture, but we learned that most of instructions use data in register file. Okay, so register file is here. And then only load or store instructions transfer data between register file and DRAM. And then other instructions like add, type instructions like add, sub, some other instructions just to use the data inside of a register file. So actually we learned about the memory hierarchy. Okay. So we already know that usually, so most of our data exists in storage systems like SSD or HDD. And then in chapter 2, I explained how the applications are executed by computer systems. So the data inside of SSD or HDD is transferred to the DRAM. So the data is stored in the DRAM. But in chapter 4, we learned that most of the instructions use data inside of register file. And then in order to use the data in this DRAM, we just use the load and store instructions. Okay. So actually we learned about the memory hierarchy. So memory hierarchy means that there are different types of memories in the computer systems, but these different kinds of memory systems have hierarchy. So that means that different levels of usage. Okay. So data is transferred from storage to the DRAM, and so the data is transferred from DRAM to register file. This is the kind of memory hierarchy. And then why locality is exploited by this memory hierarchy? So then the first question is that why do we need to use memory hierarchy? So this figure shows some typical hierarchy of our memory systems. So this is the memory hierarchy. So hierarchy means 계층 구조 in Korean. So 계층. So the hierarchy means that this is the high level. Okay, and this is low level. So usually in the society, the hierarchy means that the high level means some kings or queens or some noble people, and then low level means there's like slaves, a servant, so some this low level of some people, and then in the computer system is just a machine, like it's a device. So high level means that. So actually in our computer systems, our processor is on the RF. So actually it's not actually processor, it's a kind of a processing engine, right? Processing engine is here, so like ALU. So in chapter 4, we learned that the most of data is processed by ALU with the R-type instruction. So actually in our computer systems, processing engine is here, the highest level of the hierarchy. And then, so So register file is here. We do not learn about the cache yet, but cache memory is here. In the main memory, like DRAM is here and storage is here. So why do we need to use memory hierarchy? Because we do not have perfect memory. What's perfect memory? We do not have perfect memory. So what is the property of a perfect memory? So think like this. So which memory do you prefer? So if you want to add memories in your computer system, which type of memory do you want? You want fast memory, like DDR5. DDR5 is faster than DDR4. Also, we want large memory. So we want large space in our memories, and also we want fast memory. And then also if the cost is cheap, the cost is low, that means the price is low, then it's the perfect memory. So what is the characteristics? What is the characteristics of a perfect memory? Fast, the high performance, large, so high capacity, and cheap. Okay, low cost. So this is the perfect memory everyone wants to buy, but we cannot buy this perfect memory in the real world. So what does that mean? So if the memory performance is very high, that means that it's a fast memory, then the cost is high, and also the density is low. So that means that with this high performance memory, we cannot make large memory, okay? Because the fast, but the size of the memory is small, okay? And how about some low performance memory? For the low performance memory, the size is very large and the cost is low, so the price is cheap, but it's very, very, very slow. Okay, so it's a low performance. So problem is that we do not have perfect memory. So if the memory is fast, that means that the memory has high performance, then the density is small. So capacity is low. And then if the memory is slow, so very, very slow, then we can enjoy the high capacity, so large memory. So what's the example of this fast and small memory? Actually, in our computer system, usually DRAM. So, the DRAM is still expensive. It's more expensive than hard disk drive or flash memory. But DRAM is faster than SSD or hard disk drive. And then what's the example of the slow and large memory? It's HDD or SSD. Okay. So we have only two kinds of memory, fast and small memory, and slow and large memory. And then using these two different types of memory, we need to organize our computer systems for achieving higher performance. Okay, that's why we need to use memory hierarchy. So let's see the property of memories in the different types of memories in our memory hierarchy. So this is the register file. So as you know, the size of the register file is very small, but the register file is very fast. So think like this. So we learned about process architecture in chapter 4, and then RF. The register file is in the ID stage. So, in the ID stage, instructions access data within one clock cycle, period. Okay. So, and then, the clock frequency of the normal CPU, the commodity CPU, is about 3 gigahertz so, and then recently it reached the 5 gigahertz by Intel. So, the clock frequency is very fast, it's very high. But because the register file is very fast, we can read data from register file within one clock period. But the size is very small. In the RISC-V, the number of architectural register is just 32. Okay, so very small. Then we do not learn about the cache, but I believe some of you already knows about some different levels of cache, L1, L2, L3 caches. So usually L1 cache, size of the L1 cache is the small, and then size of the L3 cache is large. But compared to the main memory, the cache size is small. Okay. But cache is faster than memory. Okay. So, so if you just compare the specification of the commodity CPUs, then you can find that server CPUs have very large cache memories, or the expensive CPU, the high-end CPU has also very large cache memories. Okay, cache, but size is smaller than main memory in the DRAM. So we usually use the 4 gigabyte to 6 gigabyte or 8 gigabyte of the DRAM in our smartphones, laptop, or desktop computers. Okay. So compared to the cache memory, the size of the main memory is large, very large, but the speed is low. Okay. How about the storage, SSD or HDD? So if you use if you see the specification of the HDD, hard disk drive, then you can find that, usually we can use the 2 terabyte of the HDD in our computer systems. It's very, very large, but so slow compared to the other types of memories. Okay. But so this is the memory hierarchy. In the low level of the hierarchy, we use the low cost, low performance, and high capacity of memories. And then for the higher level of hierarchy, we use high cost, high performance, and low capacity memories. And then actually this is good for the performance of computer systems. Why? Why? Why do you use high cost, high performance, and low capacity memories in the higher level of the memory hierarchy? And then why do we use low cost, low performance, and high capacity of memory in the low level of hierarchy? Why? It's because we can make use of locality. So in the previous slide here, in the previous slide, I explained about the locality observed in normal applications. So that means that the data will be reused, or neighbor data will be referenced in the near future. So that means, so this is the time. So it's some execution time of a certain application. And then if a certain data is accessed at this time, And then with the high probability in the near future, same data or neighbor data will be accessed with high probability. So that means if a data is used, and then this data or neighbor data will be reused again and again. So this actually, the amount of this data is small compared to the entire data in our computer systems. So actually the size of the hard disk drive in our computer system is 2 terabytes, but we do not use entire data inside of this hard disk drive, right? We just use the part of data. So that means if we can store, if we store these frequently used data in the higher level of the memory hierarchy, so it will be frequently used, then we can enjoy high performance memory in our computer system, right? So frequently used data stored in the higher level of the memory, like register is a special memory, or like cache memory. So frequently used data is stored in the cache memory because the cache is fast. But the entire data is stored in the hard disk drive or solid SSD, but we do not use this entire data. Okay, so only required data is transferred to the main memory here, and then part of data is transferred to the cache, the higher level memory, and then if this data is stored in the cache, this data will be frequently referenced again and again. Okay, so I mentioned the data will be referenced again and again. That is the locality. So memory hierarchy is designed for making use of locality observed in our normal applications. I said normal applications. So some applications do not exhibit this locality, but usually normal applications exhibit locality, data locality. Then memory hierarchy is designed for making use of this locality. Okay, so just remember this property of the memory hierarchy. This is very important. Okay, it's a high cost. So good memory is located in the higher level of the hierarchy, and then not it's not bad because it's good for the capacity, but the low performance memory is located lower level of hierarchy. Okay, it's important. Okay, so this slide also explains the locality and the memory hierarchy of the computer system. And then in this slide, just remember the hit and miss. So in the previous class, I mentioned that we will use hit and miss frequently in chapter 5. So just remember the meaning of hit and miss. So actually the storage is managed by operating system. So, and then usually the main memory is managed by hardware. So we just focus on the main memory. Okay. So this is the main memory, and then this is cache. And then we assume that entire data is stored in the main memory. Okay. So actually the address means address of the data represent the address of address in the main memory. So actually it's a virtual memory. So just think like that entire data is stored in the main memory. Okay, it's not true, but But let us assume that entire data is stored in the main memory, okay? But this is the cache memory. So actually, when in the chapter 2, when I explain about the process architecture and then the definition of the computer system, so I mentioned that the state of the computer system is the data inside of the computer system. That means the data in register file and main memory. Okay, the cache is actually temporary memory. But why do we use cache? We use cache to improve the performance and then to exploit the data locality in our applications. Okay. So entire data is here, and then only part of data is temporarily stored in the cache memories. Okay. So, and then processor wants to, so let us assume that this processor wants to transfer data from main memory to the register file. Okay. But this cache is the temporary storage space. So, and then frequently used data is stored in the cache memory. And then this cache is faster than the main memory. It's much faster. Okay. So the frequently used data is stored in the cache memory. So processor just execute the load instruction, and then this load instruction first check cache memories, because this is fast. But we know the entire data is in the main memory. So that means that if the data requested by this processor can be found in cache or not. So because cache has only part of data. Understand? So because the cache has only part of data, the requested data can be found or not found in cache. So I frequently use this $mark for the cache because actually the pronunciation of the cache is similar to cache. Okay, 현금. So I frequently use this mark, and then actually many computer architects use this $mark for cache memories. Okay, so the request data can be found in cache memory or not, because only part of data exists in cache. And so if the data is found in cache, this is called hit. Then if the requested data is not found in the cache, this event is called miss. Okay, just to remember the meaning of hit and miss. So what are the meanings of hit and miss in the previous class? So like branch prediction. So if the prediction is correct, that is called hit. If the prediction is wrong, then it's called miss. And then in the cache memory, if the data is found in cache, this event is called hit. And if the data is not found in the cache, this event is called miss. So what is the next operation if the event is hit? It's simple. Data is found in the cache. So the data will be transferred to the processor happily, because because the data the processor can access the requested data very quickly because the data is found in cache. But for the miss case, the data is not found in the cache. So that means the processor need to access low-level caches or main memory for this miss case. Okay, until the data is found in the memory, right? Understand? So for the miss case, the processor check the low level of memory. Okay. So also this we can define the hit ratio. So this means the number of hits divided by number of total accesses. This is called the hit ratio. Then what is the miss ratio? Number of misses divided by total number of accesses. Okay, and then the miss ratio is the 1 minus hit ratio, because there are only two cases, two different events, hit or misses, when the cache is accessed by processor. Okay, so just remember hit and miss in the memory hierarchy. Okay, so I will briefly explain about the memory technology. So and then as I mentioned, there are different types of memory. So this slide explains different types of memory. So SRAM is the fastest and most expensive memory. And then usually the SRAM is called the on-chip memory. So it's called the on-chip memory because actually the technology, the CMOS technology used by this SRAM is similar to the technology used for processor design, so digital designs. So actually the same processor, same processing, same technology processing is used for SRAM and digital designs. So SRAM is typically implemented inside of a chip. So this SRAM is usually called the on-chip memory. But SRAM is very fast and it's very, very expensive. Okay. Okay. So this usually we use the SRAM for register file or caches. And how about the dynamic RAM? So I believe most of you knows that. So DRAM is used for main memory in the computer systems, but the performance of DRAM is lower than the SRAM. So this is the typical latency of the SRAM, and then this is the typical latency of DRAM. So usually the DRAM is the kind of tens nanosecond of latency, but the SRAM is very fast because the RF is accessed by 3 to 5 gigahertz of clock signals. Okay, so but compared to the other storage memory, then DRAM is also very fast. How about the magnetic disk? So we use the magnetic disk for the storage media of the hard disk drive, and you can find that the latency of the magnetic disk is like millisecond unit, like tens millisecond, but it's very cheap, so density is very high. So there are different kinds of memories and different memory technologies. So this static RAM is located in the higher level of the memory hierarchy, and then the magnetic disk or flash memory is located on the low level of the hierarchy. So actually, this DRAM technology is the out of scope of this course, where I briefly explain about the DRAM. So if you took the digital system, this the logic design course, then I believe you can you learned about the typical memory structure. The typical memory structure is composed of word line and bit line. It's called BL. It's bit line, and then the memory cell is located between word line and bit line. Okay, so we use word line to activate a certain memory cell, activate a memory cell. And then we use bit line for the data transfer. So data read and write. So with the word line, the memory cell is activated. And then if the memory cell is activated, then through this bit line, the data can be read or data can be written to the memory cell. Okay. And then actually the different memory tech. So this is the typical memory structure. And then different memory technology means that the technology used for this memory cell is different. Okay. So how about the DRAM? So DRAM, this is the word line of the DRAM. DRAM just word line just activate this NMOS transistor, and then this is capacitor, and then the word line is connected to the gate of the NMOS transistor, and then one node of the NMOS transistor is connected to the capacitor, and then another node is connected to the bit line. This is the typical cell structure of DRAM. It's like dynamic memory. So actually the charges, the electric charges are stored in this capacitor, and then based on this word line, these charges can be transferred to the bit line, or the charge is stored in the capacitor through the bit line. So this is the typical structure of the DRAM. Okay. So and then I explained that the DRAM has the low performance. So that means that the latency is higher than the SRAM. So usually we just identify 1 and 0 of this data stored in this memory cell of the DRAM using voltage level. Okay, so voltage is high, that means 1. The voltage is low, that means 0. And then this voltage is determined by amount of charges stored in this capacitor. But these charges can be dissipated, so that means that it is removed by time. So it is called dissipated. So we frequently refresh this content of the DRAM. So refresh means that the DRAM cell is rewritten with the same data. Okay, so that is called the refresh. So DRAM also requires the refresh period, and then during this refresh period, we cannot use these DRAM cells. Okay, that's why the performance of the DRAM is influenced by refresh period. Okay, and then and then I believe some of you already know about the DDR, double data rate DRAM. So we can use the rising edge and then falling edge of the DRAM clock signal for the DDR RAM. So with this DDR DRAM, then we can increase the bandwidth, data bandwidth between DRAM and processor. And then we can also use the QDR, it's a quad data rate DRAM. And usually GDDR, like graphics DDR. So DRAM used for GPU actually use the QDR DRAM. Okay. So then this slide shows the some performance of the DRAM by years, and then this T represent the some required time to process to service the some DRAM commands to the DRAM chips. So as you can see, this time is reduced. So that means that the DRAM speed is increased. The performance of the DRAM is increased year by year. Also, the capacity is increased because of the advanced in CMOS technology node, and then the price cost is also reduced. But you need to remember that I explained that for the SRAM, we use the same technology to the processor design, like digital design. But the process node for DRAM is different. Okay. So usually DRAM is slow, and then SRAM is fast, including digital logics. So that means the processor is very fast, but this DRAM is slow. It's fast and slow. Oh, you may think, oh, DRAM speed is enhanced year by year, so we can use very fast DRAM recently. But compared to the speed of the processor, like a clock frequencies used in the processor, the clock frequency of the DRAM or some performance of the DRAM is low. So that means that the DRAM is still slower than processor. Okay. So what's the problem? DRAM is slow. Process is fast. But DRAM is slow. What's the problem? So entire data is stored in the DRAM. Then, but DRAM is very slow. So the performance of computer system is determined by slow DRAM. And then this is called memory wall. So memory wall means that because of slow DRAM or slow memory, the performance of computer systems are determined by these slow memories. Okay, this is the memory wall. But then how can you solve this problem? So actually this technology is very also critical for the computer systems. So think like this. This is the worker. This is a worker. But this worker is very slow. It's slow. But another worker, A, the B, this worker is fast. But worker A need to receive result from worker B. So how can we increase the performance for this case? A is fast, B is slow, but A need to receive result from B. We can increase number of B workers. How? Then A can just give command, the same command, the command to the worker B's, and then with the time sharing manner, the A can receive the result from B. Okay. This technique can be also applied to memory systems. So I said that DRAM is very slow, the processor is very fast, but processor need to receive data from DRAM. And how can we increase the performance? We can have many DRAMs, actually many DRAM partitions. DRAM partitions. And then this is the processor. This is the DRAM memory. So if there are many partitions of DRAM, then processor can give command, that it's a request to the each of DRAM partitions, and then receive the data from these multiple partitions sequentially. So this technique is called the Theorem Interleaving. Okay, and so this is the interleaved memory organization. So my writing is not good. So let's see that this A, B, C cases. So this is the processor, this is the memory like DRAM, and then so memory. So, the processor is very fast, and then actually the DRAM bus is narrow. So the narrow means that the number of pins connected to the processor. So if you see the inside of the computer system, then you can find that this is the processor, and then this is the DRAM DIMMs, and then DRAM DIMMs are connected to CPUs with many wires. Okay, so if the bus is narrow, then we can just use the small number of pins, because the pin is very expensive. So it's a very precious resource in the computer systems. So we cannot use many pins actually. So the bus is narrow, but what's the problem? And then only one DRAM is connected to this bus. Problem is that because the DRAM is very slow, it will take very long time to receive data from the DRAM sequentially. So and then so if we increase the bandwidth of the DRAM bus, that means that we can increase the number of pins that connect CPU and DRAMs. So bandwidth is increased. So we can use the very wide DRAM. Then we can increase also performance. Okay, here. But what's the problem? The cost is very high, because I said that pin is the very precious resource in the computer system. So we cannot increase the number of pins. It's very hard. So it's very expensive. So, but if we just partitions the DRAM to the multiple partitions, then we can use the small number of pins. So that means that the memory bus is the same to this case A, but there are multiple partitions. So But this is okay because this memory is very slow. So that means that if a command is given to this one of the partitions of this DRAM memory, then this partition will service the data after very long time. So during this time, the bus is not used, and then during this time, the process can give another command, so another request to the other partitions. So it's like this. This is the processor, and then processor gives request to the memory 0. And then it will take a very long time, and then data will be out after very time delta t. Oops. And then during this delta t, this bus is not used. Okay, so processor can give another request to the DRAM partition 1. So it will take a very long time here, then 2 here, and here. So 0, the request 0 is here, then request is serviced in the here, then request 1 is here, then serviced here, 2 serviced, 3 serviced. So because this time is very long, then computer processor can give commands sequentially, and then the output is serviced from the multiple partitions also sequentially. So the bus with this narrow bus, then this data will be transferred to the, can be transferred to this processor sequentially. Then this technique is called the Theorem Interleaving. Also, in other words, this is called the memory level parallelism. Okay, memory level parallelism. So with the multiple partitions of the theorem, then we can enjoy the similar performance with this wider bus with the narrower bus. So this technique is very important for the computer systems. So this is the example. So this is the case B, and then let us assume that so it will take 1 cycle to access the cache, and then it will take 15 cycles to access memory. And then if the miss happens that is cache, so we consume 1 cycle for accessing cache, and then we will consume 15 cycles for accessing this memory. And then the entire data, so forward, is transferred to this cache and entirely. So entire data will be transferred to the cache. Okay, so it will take only 15 cycles. So for this miss event, it will take 17 bus cycles, but the data, the size of transport data is forward. So the required, the bandwidth for this case is the 16 byte divided by 13 cycles. So it's the number of cycles, then this is the size of data. So this bandwidth is about the 0.94 byte per cycle. So this is the average amount of data transferred per cycle. Okay, but for the case C, this is the interleaved memory organization. So So miss penalty is that the 1 is for accessing this cache, and then 15 is the latency of this memory. And then like this figure, with this narrow bus, the data is sequentially transferred to the processor. So we need the 4 cycles to transfer forward. Okay, that's why this becomes the 4 multiplied by 1. So entire required cycle is the 20 bus cycles, and then bandwidth is the 0.8. So it's compared to the bandwidth is low, but it's not 1/4. So compared to this organization, this configuration used the very wide memory bus is 4 times wider than this configuration. But if we just compare the bandwidth is about the 0.94 divided by 0.8. It's much smaller than 4. Okay. So because the memory is very slow, so we can use the interleaved memory organization. Okay. Then I briefly explain about the flash memory. And then recently we used the flash memory as the storage media of the SSD, solid state drive. And then compared to the magnetic disks, the latency of the flash memory is very low. So that means that it's very fast. But the flash memory is 100 times, 1,000 times faster than disk, but it's still slower than the DRAM. It's about the 1,000 times slower than DRAM. But it's cheap. It's more expensive than magnetic disks, but the price of the flash memory is cheaper than DRAM. So we frequently use this flash memory as the media of the storage media of the SSD. So this is figure shows the photo of the SSD. Then you can find that this is the flash memory packages. Okay, these are the flash memory packages. So and then there are different kinds of flash memories like NOR flash or NAND flashes. And then we frequently use this NAND flash as the storage media of the SSD. So NOR flash is actually it's very similar to the usual memories. So actually we use this NOR flash memory as the very fast storage media. So like for the storage media for firmware, and then we use the NAND flash memories for the storage media of the main storage systems like SSD. Okay. But what is the disadvantages of flash memory? Flash memory cells wears out after thousands of accesses. So that means that the flash memory cells will break if we write about 1,000 times. So that means that the cells are broken, that we cannot use these broken cells anymore. So that means that the space of the available space in the SSD, like flash memory, is decreased by time. But we not to avoid this case, we applied some well leveling technology in our SSD, but this is out of the scope of also this course. So if you are interested, then you can take storage system architecture course in the graduate school. Okay, and then disk. So disk. So disk is the hard disk drive used some magnetic disk as the main storage media, and then this magnetic disk looks like a plate. So that's why this disk is called the platter. Okay, It's called the platter. Actually, the data is stored in the surface of this one platter. Okay. And then so this, then as you can see, this is the photo of the HDD, and you can find that this platter rotates in the one direction, and then this arm change the location of the head under this platter. So actually the HDD has the mechanical part. That's why HDD is very slow. So if you see that this access time example of the hard disk drive, then you can find that so this seek time is also determined by location of the head. Then also this is the rotation latency. Then so as you can see, this is seek time, and then the rotation latency occupies the very large amount of the access time. So hard disk drive is very, very slow, but it's cheaper than flash memory. Okay. Okay, so in this time, so in the today's class, I explained about the data locality. So you need to remember. And then also I explained about the basic memory hierarchy, and then why the memory hierarchy exploits the data locality. Then also I briefly explained about some various types of memories in computer systems. Then in the next class, I will explain about the cache. Okay, cache is also very critical topic. It's a very important topic of this course. Okay, so 기대하세요. So I stop here. And do you have any questions? Okay, thank you for your attention. So see you in the next class.